Hey, this is Chris Deline from NREL. Thank you for your interest in this PVSC virtual presentation. I'll be presenting on the PV Fleet Performance Data Initiative, giving some preliminary results and talking about our methodology. A big shout out to my co-authors here. I'd like to point out that this is still a work in progress, so the results we're presenting are preliminary and subject to change, so please keep an eye out for future updates. The PV Performance and Reliability Group at NREL is focused on bringing best practice software and analysis tools to the community. Our flagship product is RD Tools, which is an open source Python platform for performance loss rate analysis. Also, we're looking into soiling and availability for inverters. We're always interested in what needs are out there in the industry, so please reach out to us. Let us know how we can help you out. From data sharing to standards and methods, we're here for you. The PV Fleet Performance Data Initiative was started about a year ago as a collaboration between the national labs, third-party data owners, and the Department of Energy. The idea is to use the capabilities of the national labs to anonymize and aggregate proprietary production data and to develop best practice analysis methods. In return for providing access to proprietary fleet production data, the individual owners in return would receive analysis specific to their own fleet. This includes degradation rate and loss factor analysis, which can help them perhaps identify lagging systems. In return, on the public side, once the data was aggregated and anonymized, overall distributions can be presented for the fleet as a whole. So this would help with pro forma model assessments so that people are using appropriate values when they're doing performance models. It can also help to identify trends versus system configuration, climate, location, technology, etc. So we really encourage anybody that's interested in more details to go to this website, as well as fleet owners that may have production data to share. The motivation for this project is that on the module side, things are reasonably well understood through a lot of research. So for instance, cell level effects can lead to degradation, broken cells, things happening inside the PV junction, such as LID, LETID. There's also packaging effects for backsheet delamination or moisture ingress. When you get to large systems, though, all of these effects are present, plus additional system level effects. So that can include maintenance issues, downtime, inverter problems. You can also have high DC to AC clipping and curtailment, which affects measured degradation rates. You can also have more prevalent data issues with large-scale systems than you might have with smaller, well-tended systems. The upshot is that when you identify the system degradation rate, you end up with all of these module level degradation effects plus system level losses, outages, tracker pointing errors, and string outages. So the degradation rate can be considerably different for large systems versus modules. So there's been several publications. There's a widely cited paper here from Dirk Jordan that's saying that at the module level, degradation rates are often on the order of half to 0.7% per year. These are also widely seen in, for instance, PV-Syst models when someone's trying to propose a new project as a project developer. But is this the right number to be using for system-wide degradation? There have been several previous publications on system level degradation, but there's a pretty wide range. Are we looking at a very small change relative to module level degradation rates, or is it a much more significant loss rate such that maybe people are not going to be getting the return on investment that they're expecting? So the motivation here is to be able to collect and publish on some of these system level degradation loss values. A little bit of detail on the fleet analysis process. So we start by collecting production data, both time series performance and system data from our third-party data partners. This is stored in a cloud-based database to make it easier for our web-based analysis methods. We then have a very important stage, which is the initial data quality checks and data scrubbing. Because our analysis is semi-automated and it operates on a large scale, we're looking at tens of thousands of data channels, it's important that we're automatically excluding channels that might have non-physical data gaps or large data shifts in them that might affect the overall results. So once we have high confidence in our data quality, we'll run several analysis tools. The main thing that we're focusing on here today is degradation rate analysis. This is through our open source Python toolkit RD tools, but we're also looking at inverter availability, and in the future we'll be looking at, for instance, soiling. So once we have these results, we will produce public and private versions of reports. This is to assist the data owners in accurate assessment of their system performance, but also to let some of these allow some of these results to be made public in an aggregated form. Some of the data quality checks that we're looking for can be shown here. So the first is an obvious jump in production data. So this is a change point detection where we can identify and reject a portion of this data stream because of the unphysical configuration change. We're also validating metadata, for instance, by checking whether plane of array irradiance sensors are in fact in the plane of array by comparing it with modeled or satellite-based irradiance measurements. We can also update and validate our site metadata by comparison with satellite imagery to double check latitude, longitude information. Also, we're working towards tilt and azimuth validation from satellite imagery. So these are useful routines, and we're working to make them publicly available through a collaboration with the PVLib team over at Sandia. And so please keep posted here to get more details. The next stage following data quality is to run analysis on each of the inverter channels that we have. The degradation analysis is presented in more detail in previous publications. We have links below, but in short, the time series data is normalized by comparison with a PV Watts model that takes account for temperature and irradiance. We then roll up the data daily and do a year-on-year comparison rather than a single least squares fit through the data. We're actually taking multiple annual slopes where we compare the performance January 1 in 1 year with the 1st of January the following year, and so on for 365 days per year. So this gives you a distribution that you can see on the right of daily annual degradation rate values. So you then compile these values, gives a median value, which is the best estimate of the overall degradation. The width of this distribution gives you information about your confidence intervals. So we run this type of analysis for each system. We're also looking at other loss factors such as availability for the system. We'll talk about those in a minute. The fleet distribution is shown here. We have over 1,300 separate sites. Many of these are larger systems, so we have over 12,000 inverters of 1.2 gigawatts capacity. The average system size is 900 kilowatts, so these are larger systems, both commercial rooftop and free field utility scale systems. The average system age is around 5 years. You'll see the module technology breakdown here. The majority is silicon. We do have a smattering of thin film modules represented. The overall fleet distribution of degradation rate is shown here. These are cumulative degradation for each of the almost 3,000 inverter channels that have passed data quality. Here, this is a preliminary result. We have more data coming in and we're refining our process, but to date, this is the median degradation rate we're showing is around 0.7% per year. So that's in keeping with previously presented, previously published results. You'll see that there is quite a wide distribution here, so some of these outlier systems we'll be addressing later. We do not expect those to be actually increasing at 10% per year or degrading at quite a rapid rate. That's likely a data quality issue. We can break this down further by system size. This is looking at larger systems greater than 1 megawatt versus 300 kilowatts and below. We did find statistically significant difference between these distributions, as you can see here. So this could be due to a couple of factors. As Dirk Jordan published in his 1603 paper, the larger systems tend to have faster reactive maintenance. So if you have an outage, it could be resolved more quickly with on-site staff. There may also be an effect where smaller systems include some roof-mounted systems. So perhaps there's a higher operating temperature from systems on the roof here. The next factor that we looked at was the age of the system, and this was a little bit less conclusive. We didn't see much statistically significant difference between systems that are older than 5 years versus those that are only 2 to 3 years old. We did find, though, that in the first year of operation, systems tended to have more issues. This could be either due to phased staged turn-on or perhaps issues that were resolved within the first year or temporary LID type effects. But for systems beyond 2 to 3 years old, we didn't see much statistically significant difference. Some of the context for the outliers that were shown in earlier plots. This is a system that had a 10% per year apparent degradation rate, but it's pretty clear that it's seasonal soiling that's causing this pretty large loss rate. The trend we've seen is that for systems with short durations of data, only a couple of years, any instance of data outage or intermittent performance such as this would be exacerbated in the trend analysis. So we would expect this to revert closer to the mean while with additional data. This is another example where data configuration change wasn't caught with our change point detection, and so this resulted in an extremely high 28% per year positive performance change with time. Obviously that's not physical, so we would expect with more data and higher accuracy quality routines, we would remove some of these outlier systems. For that reason, we're not paying much attention to P90, P10 type statistics at this point in time. Another factor that we looked at was inverter downtime and availability. The methodology is going to be presented in more detail by this talk that you see below, also here at PVSC by Kevin Anderson. So please check that out for more detail. But here we're taking a look at outages and times of either lost production and lost data from PV inverters. We did find that inverter outage and downtime was most likely to happen in the first years or months of a system's performance. So here this is comparing incidents of inverter downtime versus the quantile of that system's life. It's pretty clear that there's a decreasing trend. In particular, the majority of outages occur in the first 10% of system lifetime. So this has implications on calculating degradation rates. If these are not accurately rejected from the data analysis, it would erroneously make it appear that performance is low in the beginning years and increases, so it could actually give you a positive degradation rate. As we continue our work, keep an eye out for updated methodology and results at future conferences. In particular, we're working towards a public dashboard for distribution visualization so people can dig into final results in detail. And that's it. So thank you for your attention. Thank you to our project partners and to DOE for their support. For more information, please check out the full report here or just shoot me an email. Be safe out there, everyone.